Next topic is manifold learning. Okay, usually manifold learning means the non-linear dimension reduction algorithms, and they find invariant property of a data set. And when the manifold is linear, then we can apply linear methods like PCA, MDA, and ICA, NMF, etc. And also we can think of non-linear methods like kernel PCA, kernel FD, Isomap, LLE. Usually when people say manifold learning algorithms, they mean Isomap or LLE or stochastic neighbor embedding, etc. Okay, these PCA and LDA, ICA, NMF, kernel PCA, usually people don't call them manifold learning, but in a sense, they are kind of part of this manifold learning. Okay, so what is a manifold actually? Think about this globe. Okay, so we have a map from the 3D. Okay, it means this two-dimensional space is actually embedded in the three-dimensional space like this. Okay, then this manifold is defined as differentiable space where locally Euclidean. Okay, that is definition of manifold. So look at this globe. If we zoom in a lot, then it's flat. Okay, it's a flat land. So everything is Euclidean there. Okay, think about your table. So table is flat. But if we zoom out, then it is curved, right? But anyway, locally Euclidean, and then this two-dimensional space is embedded in the high-dimensional space. Okay. And here is another figure. So when this image is rotated, then let's think about this image. Okay, let's say 10 by 10 image. Then this space is 100 dimensional space. And when this image rotated, then this one is moving in this 100 dimensional space slightly, and probably the rotation of this image will make a curved manifold like this. Okay, it will not be a straight line, obviously, and there is other kind of factors instead of rotations. How about changing illumination, or how about changing orientation? Okay, then based on those factors, we can generate other from this image. Okay, then we can generate some other curve. And if we change both factors at the same time, then probably we will have something like two-dimensional hypersurface. Okay. And then long time ago, like in 2004, there was a paper saying the manifold learning algorithms are actually kernel machines. Okay, that was proposed in 2004. And we had the same idea. Okay, then we proposed some papers about this. So I'm going to talk about it later. Anyway, manifold learning is actually kernel machines. And before talking about these manifold learning algorithms, let me point out one important thing. So PSD, positive semi-definite, is necessary and sufficient to be a metric which defines a distance function. Again, if we define one kernel function, we defined inner product matrix in the high-dimensional space, and if we define the inner product matrix, then we can derive a distance between data points. Okay, if we know the inner products, then we know the distance. If we know the distance, then we know the inner product. Okay, So they are kind of equivalent. So in general, metric, kernel, and distance and covariance all are equivalent. And in a sense that they define a manifold by defining relations between points. So here's the thing. If we define the distance between the data points, then we can estimate what kind of manifold where they lie. Okay, so let's say this is the data manifold, and data samples are located like this. And if we know the distance between the data samples, okay, if we know the distances between the data samples, then we can guess what kind of manifolds. Okay, and if we know the covariance, then so they are all equivalent. If we know the covariance, then we can derive distance and inner product and kernels, and we can guess how these data samples are located. And in manifold learnings, we have, as I said, we have a linear manifold learning. Usually we don't call them a manifold learning though. Okay, as a nonlinear manifold learning algorithms, we have two representative algorithms, Isomap and locally linear embedding. But in 2008, the stochastic neighbor embedding was proposed by Martin and Hinton. If you are studying deep learning, then you might have heard a lot about Jeff Hinton. Okay, so before deep learning, then Jeff Hinton was also working on manifold learning algorithms too, and Yosha Benjo has published a couple of papers in the manifold learning too. Okay, and then there are lots of algorithms, Laplacian eigenmaps and semi-definite embeddings and the fusion maps, Hessian eigenmaps, and stochastic. I already said that, and the locality preserving projections, etc., and so on. And this deep autoencoder is actually neural network based manifold learning algorithm, or neural network based nonlinear dimension reduction algorithm. So we are going to talk about this one later. Okay. Other than that, all the other methods are traditional manifold learning algorithms, which means these algorithms can be interpreted as kernel machines. Okay, which means all these are solved based on eigendecompositions most of the time. Okay, in manifold learning, there are a couple of assumptions. Okay, so first of all, we think data samples were generated by transformation of the parameters in a latent space. So these are parameters. So if this one is one point is a face image, okay, then x1 is rotation, and x2 is up and down or something. So if we change these two parameters, let's say this one is rotation, then this one is a 0, then this one is positive angle and negative, and this is 0, this one is up, and this one is down. So if we control these two parameters, then we can generate some face images. So from here, based on the rotations, then we can generate these samples, and based on up and down, then we can generate this sample. If we change both, then we can generate these samples too. So when we observe some data samples, then we assume that these data samples are from these two hyperparameters. Okay, and based on the nonlinear function. And for a nonlinear method, there are more assumptions. The samples should be dense enough. Okay, so the data samples should be like this. But if we have some data samples like this, and they are not connected, they're kind of sparse. We have empty space around here between these data samples and these data samples, and they are not connected. then we cannot apply manifold learning algorithms. So basically these samples should be dense and they should be connected. So we need lots of data samples between these two. Okay. And again, as I said, by definition, the definition of manifold learning assumes that everything is locally Euclidean. Okay. If we zoom in really closely, then this is Euclidean. Even though the manifold is really sharp, then if you zoom in here, locally it is Euclidean. Okay, it's flat. It is flat line. If you zoom in a lot. Okay, the first representative algorithm is Isomap. Okay, and the manifold learning algorithms are to find the embedded manifold from data samples in a high-dimensional space. There's general statement about manifold learning algorithms, and let's say this is true manifold in the three-dimensional space, and we don't have any idea about this. Okay, we observe data samples. Okay, from these three-dimensional data samples, we have to reconstruct a two-dimensional representation like this, and then by the way, the name of this kind of data set is a Swiss roll data set. It looks like a Swiss roll, the snack. Okay, so given this Swiss roll data samples, then we want to unfold these samples into two-dimensional space. And Isomap is perfect to do this. And Isomap algorithm is really simple. It's super simple. Okay, so basically Isomap uses MDS. Okay, so MDS says as long as we know the distance between the data samples, then we can project the data samples into coordinate. Okay, and if we use a few eigenvectors, then we can project the data samples into low-dimensional space. Okay, so Isomap uses MDS, and the question is how to define the distance between the data samples. And Isomap uses geodesic distances on a neighborhood graph. That's it. So geodesic distances and MDS. That is Isomap. And then how can we get this geodesic distance? Oh, by the way, what is the geodesic distance? On this globe, we have Korea here, and the opposite, we have Argentina. Okay, from South Korea to Argentina, how to get there? We cannot go through this planet, globe, right? We cannot go through this Earth. We have to follow this manifold. Okay, then what is the shortest path? That is this length. Okay, so geodesic distance is the shortest path on the manifold. If we have data samples like this in this figure, from this point to this point, what is the distance? The Euclidean distance says this. But if we calculate Euclidean distance between these 2 points, then we have to go through this empty space. So we have to get out of this manifold, and then we have to reach. And that is not possible. So we cannot get out of this manifold. So we have to follow this manifold to get here. And then the shortest path on this manifold is actually geodesic distance. So Isomap will calculate geodesic distance, and then as long as we have a distance, then we just simply apply MDS. Then the question is, how can we get this geodesic distance? First of all, construct a Euclidean distance matrix D sub E. Okay, So in this distance matrix, we calculate all the distances. So from here to here, to here, to here, even to here, we calculate all the distances. Okay, because in this case, we have no idea about the manifold. Okay, so just calculate the Euclidean distance. And then find neighbors and connect them. So from here, if we find the neighbors, then these points are neighbors, right? Okay, then just connect them and disconnect all the other data samples. Okay, and now calculate geodesic distance, which is just simply a shortest path. So we have a connected manifold, a connected graph. So all the points are connected to its neighbors, and by that these are connected and these connections are disconnected. Okay, and this one is disconnected, and we just calculate the shortest path. Okay, and then if we follow the this shortest path, and because we have only neighbors, so neighbors are connected, so if we calculate the shortest path, then we approximately get this geodesic distance. Approximately. It's not correct, but approximately. Okay, then we use this geodesic distance matrix and apply MDS. That's it. Okay, and then if we check this shortest path on this manifold, and in the unfolded manifold, this shortest path will be like this red curve, and this one is slightly different from this straight line, the blue line. Blue line is actual geodesic distance, but there's no way to get this geodesic distance, right? So we just approximate this geodesic distance based on a shortest path. Okay, Isomap algorithm is that simple. That's it. And the question is, who is my neighbor all the time? In machine learning, the question is how to define the dissimilarity and who is my neighbor. So most machine learning algorithms use local neighbors to construct a graph, and there are two approaches. We already talked about these two approaches before. First, we get the k nearest neighbors, which is more popular, and second, epsilon neighborhood. So in k nearest neighbors, we choose the k nearest neighbors. Okay, so if the red point is the point that we're interested in, then if k is 4, then from here we get the 4 nearest neighbors, these guys. Okay, good. And the other option is epsilon neighborhood. So define the epsilon first and then choose the neighbors within this epsilon. So this is epsilon. Within this epsilon we have 3 points, and then these are the neighbors. But usually we prefer this k nearest neighbors, because if we use epsilon, then epsilon depends on the data distributions. So it's not that simple. We have to probably calculate the basic the distance, the distribution of the distances, and then based on this we have to define epsilon. But if we use k nearest the neighbors, then k would be 3 or 5 or 7, depending on the total number of samples. Okay, and the k does not make much difference as long as it is in an appropriate range. Usually appropriate range would be like a 3 or 5, 7. It could be 11. Okay, but if the manifold is really noisy, then we have to minimize the data. We have to minimize the k. Okay, so if we apply Isomap, then if k is too large, then there's the short path between these two. Okay, if we have a short path, then geodesic distance is not actually cannot reflect the manifold. Look at this one. These samples and this sample. The shortest path should be like this. But if there is a shortcut here, then probably this one would be the shortest path. So we cannot increase k too much. Okay. And if you apply Isomap to face images or handwritten digits, then we can get these beautiful figures. And if we use the two-dimensional, then the first dimension would be left-right pose. Again, when we apply the machine learning algorithms, we cannot have a meaning of the coordinate automatically. In this case, after applying Isomap, then we look at the result and then we figure out, oh, this first dimension is about left to right pose, and second dimension looks like up down pose. Okay, these meanings are given by us. So machine learning algorithm usually cannot define the meaning of these coordinates, cannot automatically. And also when Isomap is applied to handwritten digits, then the first dimension looks like a top arc articulations. How curvy this digit is. And the second would be bottom loop articulations. How much curve here? In this case, we don't have any curve, and in this case, we have a lot of curve. Okay, again, these meanings are provided after Isomap. And as I said, we can interpret manifold learning algorithms as a kernel machine. Okay, and we have the same idea, so I interpreted Isomap as a kernel machine. And then if it is a kernel machine, I thought if it is a kernel machine, we can drive the kernel from Isomap, and the kernel should be positive semi-definite. Okay, if the kernel is not the positive semi-definite, this is not a kernel machine in theory. So I checked, and unfortunately, the Isomap's kernel is not positive semi-definite. So I modified the kernel to be positive semi-definite, and then I proposed the kernel Isomap, and the kernel Isomap works as if kernel Isomap is like a kernel PCA. So we can project new data samples to the same space, same low dimensional space. So based on kernel Isomap, we train and we project training samples, and then when we have a test sample, then we can project this sample in the same low dimensional space. As long as we can interpret, we can rewrite this Isomap as a kernel machine, then we can do the same thing as what we did in the kernel PCA and the kernel FD. Okay. And the next manifold learning algorithm is locally linear embedding, LLE. Okay. And in LLE, the idea is quite simple, but the equations are a little complicated. Okay. So let me explain the main idea of this algorithm. So basically, LLE keeps the neighbors. So if the data samples are neighbors in the high dimensional space, then they should be neighbors in the low dimensional space. That's a pretty simple idea, right? So, in the high dimensional space, if these 2 points are neighbors, then in low dimensional space, they should be neighbor. So to implement this idea, then there are a couple of steps. First, find neighbors. Okay, that is the first thing to do. So in the high dimensional space, find the neighbors for all the data samples. So this one has neighbors, and this one has neighbors, and this one has neighbors. So find all the neighbors for all the points. And then find the linear weight. So xi can be defined by its neighbors. How come is possible? So we assume that when we apply the manifold learning algorithms all the times locally, it should be Euclidean. If it is Euclidean locally, it means it is flat. In this flat, when we have neighbors like this, and we can define this one, and let's assume that these neighbors are really close. So when we look at these points, they are on the flat space. Okay, they are on the flat space, which means we can apply this equation, which means this point can be defined by these samples. Okay, so this one is defined by this ones, and this one is defined by these one's neighbors. Okay, and then now we can update, we can learn this parameter wik. Okay, again, in the high dimensional space, we will learn this wij. Okay, so let's assume that this w is already learned. Okay, so we know this wij, and now xi is in the high dimensional space point. Then now we have yi, which is a corresponding point in the low dimensional space, and in the low dimensional space, yi can be defined by the neighbors with the same weight. Okay, and then in this step, we know x sub I and x sub j, and we know who is neighbors, and we have to update this one. But in this step, we know who is neighbors. We have this matrix, but we don't know yi, we don't know yj. So we have to learn yi and yj. Okay, so in for the second step, we minimize this reconstruction error to find the linear weight. So we define an objective function like this. xi can be defined by its neighbors, and then we want to minimize this error for all the data samples, and wij is summed to 1. That is constraint. Okay, so now we learned the w sub ij. Then for the third step, we want to minimize this one. It looks the same, right? But in this case, w is the parameter. In this case, y is the parameter. Okay, so w is fixed at this moment, and we update yi and yj. And again, we assume that these data points are centered. And then their size, their scale is kind of constrained. Okay, so think about this one. From this high dimensional space to low dimensional space, if we increase the scale, okay, then we can have lots of ambiguity here. So we just we put one constraint to avoid this ambiguity. So centered and the same scale. And these equations are a little complicated, and we can skip this part. And if you are interested in manifold learning algorithms, then you can follow these equations line by line. Okay, And in this slide, we find y. In the previous slide, we update wi, and in this slide, we learned yi. Okay, so you can follow the lines by yourself. Okay, so then when we apply LLE to a couple of examples, then we can get a beautiful figures again. And when we apply LLE to Word document counts, then we can see this Italy and Italian and Middle Ages, medieval, and Paris, London. And here, painting, gallery, artist, painter, etc. So we can see some meaningful relationship between the words. And also, if you apply the LLE to image data set, then this axis shows the expression of this person, right? This axis shows left and right. And Isomap and LLE are the most popular representative manifold learning algorithms, but they are different. So Isomap takes a global strategy and the LLE takes local strategy. So Isomap calculates the geodesic distance between all the pairs, okay, and then it tries to it applies MDS to the geodesic distance. So when we apply MDS to geodesic distance, then all the pairs are important, and MDS take care of all the distances. Okay, even when 2 points are far from each other in the geodesic distance, but still that is important. So that's why Isomap takes a global strategy, but LLE considers only the neighbors. Okay, so neighbors are covered by LLE. And LLE analyzes local linear coefficients and reconstruction errors, and no need to solve large dynamic programming problems, which means in Isomap we have to calculate a shortest path. Okay, and W is very sparse, and whose structure can be exploited for savings in time and space. And there are a couple of more efficient algorithms, and it is closely related to spectral clustering. So we already talked about the spectral clustering, and the algorithms are similar. They look similar, okay? And that's it.